everybody. We are back with another amazing activity through PLTW. It's going to be the ETEX calculating property drainage activity. And so we've got the introduction here. They got the goals. They've got the resources as well. This is the actual PDF that I've hyperlinked in our Canvas assignment. But you do want to make sure that you have the engineering formula sheet, and also having the presentation notes up too is always very, very helpful. But we're going to go ahead and first start off with this example calculation here. And so they tell us to review that. That's the notes we went through in class. And so they end up breaking down this equation here for us, which is the peak runoff rate equation. Now, on our engineering formula sheet, we can end up scrolling down. We will find this equation to be in section 15, stormwater runoff. So whenever you're taking the EOC, if you get any stormwater drainage calculation questions, remember you can always do Control F. Just type in simply stormwater. It's going to bring you immediately there. So Q here is the peak storm runoff rate. We were talking about how Q is always used in this course, as well as most of your engineering courses, right? If not all of them, Q always represents a flow rate. Now, in this particular instance, it's the volume of water leaving the site per second. So it's cubic feet per second is what Q is. We've got CF as well. CF is the runoff coefficient adjustment factor. So that is based off of the return period of the storm that's coming through. So if it's anywhere from 1 to 10, it's going to be a 1 for the adjustment factor. If it's 25, 1.1, so on and so forth here using this table. We've also got C, which is the runoff coefficient. Remember, C is our constant, and it's based off of the material. So just like how whenever we were going through the Hazen-Williams formula, you'll see that there's C right here as well, right? That was based off of, or that is based off of the actual pipe material. And so you use a particular C value for that. It's basically the same in the fact that this C value is also based off of the material. And so we actually have the runoff coefficients here, categorized by surface, and then also by use, and then industrial we've got down there too. So if it's farmland, for instance, right here, farmland, you'll see that we have this range of values. And so what we're going to end up doing is take the average of those two values. So it'll be 0.05 plus 0.3, which gives us 0.35, which is going to be approximately 0.175, I believe. But that's our breakdown. It's good to know the equation sheet and where to be looking. So let's go ahead. Let's go through this example here. So they have calculated the site runoff. So they have supposed developer purchase a 3-acre farm in Nashville, Tennessee, in the middle of the state. As part of the project, a 30,000 square foot asphalt parking lot area will be placed on one side of the 3-acre farm. They want us to solve the rational formula to determine the peak flow of the property prior to development, which is our pre-development, right? And then after that addition of the asphalt parking lot has been added in, which is the post-development case. They want us to use a 10-year return period and 1 hour duration for the rainfall intensity for this calculation. So as we get moving along with this, they actually are going to be having us reference this website right here. And so this is going to end up providing us our table to be able to find which is the rainfall intensity. And so they have us selecting the state Tennessee, right? Because this is in Nashville. And then we're going to select the location by station using Nashville WSO Airport. So Tennessee is right here, TN. We can go by station. If you type in N on your keyboard, you'll end up seeing that the options that start with N show up. It just so happens that it's our first option that we want there. And so we're going to end up using that. And then as we scroll down, we'll see the point precipitation frequency, or PF estimates. And so we're going to end up using this for, remember, we've got a 10-year, 1 hour rainfall. And so 10-year right here, and then we've got 1 hour. So our value is going to be 2.17. So 2.17 inches per hour is what we're going to end up using. So just as they have there. We also have the area. So this is the pre-development runoff situation, right? So this is 3 acres of that farmland. And so we've got this value right here, which is C. So if we go back to this, we've got farmland in here. We got 0.05. So we can punch this into the calculator. 0.05 plus 0.3, that's going to end up giving us 0.35. If you divide that by 2, you end up with the 0.175. So 0.175, they end up averaging or rounding this up to actually be 0.18 for their calculations. CF, since this is just the 10-year storm, you'll remember CF 10-year storm return period is just 1 for that value. And so now what we can do is we can end up plugging in all of these known values. Q equals CF CIA. So we got 1 times 0.18 times 2.17, which is that rainfall intensity, multiplied by the total area, which is 3 acres. So we end up with the 1.2 CFS. Now, what does that stand for again? That is cubic feet per second. So that is the flow rate of the water off that property. So part 2 is where they have us calculating this out for post-development. Okay, so post-development is after we have added in that parking lot, right? And so they have this where the I still remains the same, right? Because it's still a 10-year return period that lasts for 1 hour. The area, they have it as 30,000 square feet. And so this is where in our equation sheet, we can type in acres, right? So we want to convert this to acres. So as you can see here, 1 acre is equal to 43,560 square feet. So they end up providing us with 30,000 square feet is what our area is of our parking lot. And if we divide that by our conversion factor here, which is 43560, that's going to end up providing us this in acres. And so if we end up going back in here, they end up rounding this up to 0.69 acres there for the parking lot. So area 2, this is the area of the farmland, right? And so since we're putting 0.69 acres of the parking lot onto this 3-acre lot, we're going to take 3 acres minus 0.69, and that will end up giving us the remaining acreage of the farmland. So it's 2.31 acres. Now for C is for the parking lot, right? And so if you end up looking at this, we can go back to our stormwater runoff section. And this is a asphalt parking lot. Now they end up saying to use the conservative coefficient for the parking lot. And so if you use the conservative one, you're going to end up putting this at the highest range there, which is 0.95 for that. So that's how we end up getting that number there. So moving on, we've also got C2. So C2, they just have us using the average coefficient for the farmland, just as we did in the pre-development. And so that's still going to be 0.18, where we're rounding that up to the nearest tenth. And what they want us to do is actually calculate a composite runoff coefficient. And so what this is basically going to do is find out the average based off of the amount of acres for each coefficient. And so what we end up finding is that this is 0.36 here. And so this is the actual equation you can end up using, just as they have here, 15.2. So that's one of the options. Remember, what you also can always end up doing is just calculating this out for the actual parking lot, and then calculating this out for the farmland section as well, where you just have a Q for the parking lot, right? Q equals CFCIA, where C and A is the C value for the parking lot, and then A is the area of that parking lot, the 0.69 acres. And then you could add on to that where your second Q value is the Q for farmland, right? So this is just another approach that they're showing us here. We can take the C value for our farmland, multiply that by the acres of the farmland, plus 0.95 times the 0.69 acres of the parking lot, right? This is the C value for the parking lot. Then what we do is we just divide that by the total acres. And so this ends up taking into consideration, as we said, right, basically an average of the C value of our whole lot, taking into consideration how much area each of those materials take up. So we end up with 0.36. And then just as they showed us here, you can end up calculating Q here. So then we use CF. And then we use that C value, which is the average C value for this lot. And then we multiply that by I, and then multiply by A. And so you'll end up with this 2.3 cubic feet per second. So then if we're trying to find the change in runoff, what we're going to end up doing is we're going to take our previous value, right? Or we're going to take the final minus the initial. And so what we basically found is that this is an increase of 1.1 cubic feet per second, right? Because we end up with 2.3 here for our post-development. You subtract that 1.2, we end up with 1.1 cubic feet per second of an increase. And so just as we talked about in class, the engineer would need to end up coming up with a stormwater management plan for the site, because obviously we don't want to end up having that additional increase of 1.1 cubic feet of water per second leaving this property for this particular storm. So Do note that the rainfall intensity is unique for each location, right? For a lot of the problems that we've done so far, it has been calculated out for Nashville, Tennessee. So you cannot confidently use charts for Nashville to determine the rainfall intensity for other locations, such as where our affordable house is going to be placed. It's in Noblesville, Indiana, right? And so we're going to need to actually reference this site next for Indiana whenever we get through our actual calculation of our affordable home. So they have us choosing the applicable state and then choose precipitation intensity as the data type and partial duration. Next, select the location and click submit. So in this case, we could go into Indiana and then we could end up finding Noblesville. So they have, what did they end up telling us to do? Choose the applicable state, precipitation intensity as the data type. So data type, precipitation intensity. And so we can end up referencing Noblesville there. And partial duration. So partial duration. Let's go back to this partial duration. Yep, nice for the time series type. And then, seems that we're bugging out here. Let's try that again. Okay. Next, select the location and then click submit. So if we're here in Noblesville, Indiana, right, we can end up running this. And so if we pop down here, we've got our actual rainfall intensity chart for Noblesville. Okay. Right here, this is just straight from the e-text. They've got all these coefficients for us that we could possibly end up using. And they also got our CF values down here. So now we're going to go ahead and move on to the actual procedure. So we're going to take into consideration where our location is. We were just talking about for the actual Noblesville, Indiana location, right? But this is for Chicago University in Chicago. So let's keep that in mind. Down to business, we've got our workout here to take note, put our name, got the title, date, and then also the class period in there. So I'm just going to be using this. Obviously, you guys will have your engineering notebook that you're going to be doing your documentation. And so what I'm going to do is I'm going to go ahead and write down some very important information here. So they want us to find the change in stormwater runoff for a 1.5 acre site near Chicago University in Chicago. So our location is going to be Chicago, Illinois. So we'll just go ahead and put this down. Number 2, location. You could even go site location, but Chicago University, Chicago, Illinois. So we've got that. Now we know that the total acreage is 1.5 acres that was forested before construction. So we also have this information here too. A 50 by 35 coffee shop with a 100-foot by 120-foot parking lot was built on this site. The remainder of this site was planted with lawn and well-drained sandy soil that has a slope of 7%. Okay, so we want to keep that in mind to the sandy soil, the 7%. The design storm is a 25-year, 1-hour storm. And they want us to use the average runoff coefficients for the forested land and the post-development lawn, but use conservative values for the post-development roof and parking lot runoff coefficient. So if it's the conservative values, we want to use that upper range there. And remember to use the runoff coefficient adjustment factor for a recurrence interval greater than 10 years. So we have the 25-year storm. So let's start off with this. So we'll put in the documentation CF. So our CF values, remember this is going to remain consistent throughout. So CF is set up for a 25-year storm is what we've got. So if we pop into our equation sheet here, we can see we've got a 25-year storm. So that's going to be 1.1 for our CF value. So I went ahead and noted that. We're going to also have total area as well that we're going to want to look at. But then I as well is what we want to find. So I'm going to go ahead and write that down. So I here, and we're going to go ahead. And so we're near Chicago University in Chicago. So let's type this in, Chicago University in Chicago. So let's see where this is So this might be fictitious. University of Chicago State. Let's end up using this location. Want to end up typing this in. And so let's see where this guy is located. So we've got this address here. Let's take a look at that. We can look at it on the map too. So we'll just say that Chicago State University is what they're referencing. Okay, so we're just right there. Okay, nice. So let's go ahead. Let's go to our PF map, the point frequency map. Here we go. So precipitation frequency data server. We're going to go Illinois. And then we're going to be up in good old Chicago. I'm going to go ahead and type this in now. We want to make sure that we have the precipitation intensity here. And then we also want to make sure that we have the partial duration. Let's go ahead and click search. Excellent. So now we've got that set up. Perfect. We've got our precipitation chart here. So we're finding I, the intensity in inches per hour. And so just as we said, we are dealing with a 25-year, 1-hour storm. So 25-year, 1-hour storm. 25-year, and we've got 1-hour storm, which what we've got here for our intensity is going to be 2.44 inches per hour. And then what I'm going to do, so I'll bring this guy back here. I'm going to put in 2.44 inches per hour. Remember, this is for a 25-year, 1-hour storm. So we're going to put that down as well. Next, we have the change in stormwater runoff. This is a 1.5 acre lot. So I'm going to just put a total, and I'm going to write that down as being 1.5 acres. So I've got that underneath this guy. So we got 1.5 acres. Starts off for pre-development, right? And this is forested land. So this is pre-development. We could put this in here, pre-development. And then we're going to also end up putting in here our C value. So the C value, they say, let's see here, use average runoff coefficients. So let's go ahead for forested land. They want us to use the average here. So C in this case is going to be, we can go ahead and put this down 0.059, right? 0.059 plus 0.2. 0.059 plus 0.2. Remember, we want to put the parentheses on there, divide that by 2, and so now we can end up punching this into the calculator. I'm just using the good old built-in calculator for the Mac, but remember, you can end up using that TI-84 emulator online. I'm going to divide that by 2. We end up with 0.1295. We're going to go ahead and round that to the nearest hundredths. So we're going to go 0.13 for our C value there. And so we'll end up going back into here. That was forested before construction. And so what we're seeing here, I think that this is going to be the Q pre. So we can go ahead and calculate out Q pre. And we'll just type in CFCIA here. And so we're going to have 1.1 times our C value, which is 0.13. We're going to then multiply that by, and I'm going to bring this desk view back up, 0.13 multiplied by our I value, right, which is 2.44 inches per hour. Then we're going to multiply that by A, which is our total acreage. And so now we can go ahead and get out our calculator here. 1.1 times 0.13 times 2.44 times 1.5. What we've got there for our total pre-development runoff is 0.52. And then let's go ahead and we'll round that down to 3 there. So 0.523. Remember, this is cubic feet per second. The other way you can write that down is CFS. And so that is what we end up with for our value of pre-development is 0.523. And so now what we're going to do in this next part is we're going to calculate this out for post-development, right? Where we've got this 50 by 35 coffee shop and then the 100 by 120 foot parking lot that's built on there as well. Development, so what I'm going to do here is put post-development, just to be very clear. We're calculating out the Q for the post-development. Now, do keep in mind here, Q post, it's going to be the case where we have the Q of the parking lot plus Q of our roof plus Q of the lawn and here as well. So we do want to keep that in mind. So let's just make sure that that is the case. So for certain, we have the coffee shop, we have the parking lot. The remainder of the site was planted with a lawn. Yep, so we're going to have Q of the lawn. Now remember, the lawn has the sandy soil with a slope of over 7%. So let's go ahead, let's start to set this up. We can choose first, for instance, let's go with the Q of the parking lot. Let's calculate that out. So Q of the parking lot. And so remember, this is CFCIA, where CF is going to be consistent throughout this problem because it's a 25-year storm, right, that never changes. Let me go back to here. 25-year storm that never changes. Now C, we don't know that actual C value for the parking lot, so we'll leave that one blank. Our rainfall intensity, though, that's another thing that's going to remain consistent throughout this problem, right? We have a 25-year storm that lasts for 1 hour. It's a designation we made. And then in terms of that area, we're going to also need to actually convert this. So let's first find C, and then we'll talk about that area. So C, remember, they say, this is for the parking lot. So we got the parking lot right here. They say to use that conservative values. Let's see here, conservative values for the roof and the parking lot. Yep. So now if we go into here, we've got the parking lot. Now they want us to be conservative with that. So we're going to end up using that 0.95. Keep in mind, asphalt or concrete. Let's actually check it out and let's see if they make that designation, whether it is concrete or if it is asphalt. So no, they actually don't have that for us. But taking that into consideration, 0.95 is what we want to end up using for that. So we're going to go ahead and put that C value being 0.95 because, as we were saying, that's the highest number within that range. And so that's playing it most conservative that we can. In terms of the area, let's talk about that area calculation. They have 100 foot by 120 feet. And so if we ended up doing that calculation, 100 feet multiplied by 120 feet, that's going to end up leaving us with a value that's going to be a unit of feet squared, right? And so now what we can do is we can multiply that by our conversion factor because we do need our area to be in acres. So in 1 acre, there's something like 43,560. So let's go ahead, let's test that out. Let's see what that actual value is for our conversion factor. And so we do see 1 acre, we have 43,560. So 43,560 feet squared, right? Remember, this is the case where these 2 feet, they're going to multiply by each other, right? So that's going to create feet squared. That's going to cancel with this feet squared that's underneath that. And so we're going to end up being left with acres there. And so now we can go ahead and calculate this out. So we've got it where, get the good old calculator, 1.1 times 0.95 times 2.44 times 100 times 120. And then we're going to divide that by 43,560. And so what we end up with here is going to be a value of 0.702. And remember, that is cubic feet per second for that runoff. So that's for the Q of our parking lot there. And so we're going to go ahead and write that down. Up next, we want to end up finding the Q of the roof, or we could do the Q of the lawn. Let's actually do the Q of the lawn next. So this can be CFCIA. Remember, the CF value is going to remain the same as well as I. The C value, however, we're going to have to check that out and investigate. I'm going to go ahead and write that I value in there and just leave some space for the C value. And then in terms of the area, we'll also be able to do that calculation too. So let's go ahead. Let's pop back in here. Let's find out what that C value is going to be here. And so this is for our lawn, right? And so as we were saying, this is well-drained sandy soil with a slope of over 7%. So if we go back here, we can type in our Stormwater. Oops, have a double S there. Geez, I clearly haven't had enough coffee today. So we got well-drained sandy soil, over 7% slope. We've got the 0.15 to 0.2. Now, do they tell us to be conservative with the values that we use for the lawn? They say use the average for that. And so that value that we're going to end up using is going to be that 0.15 to 0.2. And so that's going to end up giving us a value of 0.175 there, right? And so now we know what that C value is. It's 0.175. And so now we can end up calculating out our area as well of the lawn. So this is where we probably should have ended up calculating out the roof first, because to be able to calculate out the area of the lawn, that's going to be the area that we started with, right? That 1.5 acres minus that area of our parking lot, and then also minus the area of the roof. And so we're going to have to do those calculations. We're going to just put this on pause for a second. With that calculation, we're going to go to Q roof, so that then we can end up determining what those areas are of those guys. Going to end up calculating out what this actual area is for the parking lot in acres. So I got the TI-84 up over here. Going to switch to using that guy. 100 times 120. Oops, let's try that again. 100 times 120. And then that is the square footage. We've got to convert that then to acres, so 43560. So what we're going to divide that by. So this ends up being 0.2755 acres. That's what that is. So we'll take a note of that. Because just as we said, the lawn is going to end up being our total acreage that we're starting with, minus the parking lot's acreage, also minus the roof's acreage as well. And so we can go ahead and let's continue with the roof, because we can end up calculating that guy out. And so let's go ahead, get down to business here. So Q of the roof, we're going to bring that guy back up there. CFCIA. So just as we were saying, the CF value is going to remain the same. Also, our I value is going to remain the same. C will be different because it's based off of material type, right? So I is just, CF and I, they're just in relation to our storm that we're dealing with. And then we're going to have to do the conversion for the area there too. So let's go ahead, let's pop back onto this guy. And so here they end up saying, use average runoff coefficients for the forested land and the post-development lawn, but use conservative values for the post-development roof. So conservative value for the post-development roof means we're going to have to use that upper range value. And so let's go ahead and let's look at, so we got a shingle roof there. We'll have to kind of check out any of the different options. Let's see here. Yeah, it's looking to me like we're going to end up using that shingle roof value. Yeah, okay, perfect. Yeah, so the shingle roof 0.95, we are going to end up using that value, that upper range value. And now in terms of that area, we've got to calculate that out. So for our area here, we're going to end up putting it right here. They end up specifying for us, it's a 50 by 35 foot coffee shop. So we're going to take that 50 feet times 35 feet. Remember, if we multiply that out, 50 times 35, and then we have feet on there, that's going to give us feet squared. Then we can multiply that by that same conversion factor we were using previously, which will allow us to go from square feet to acres. So we'll throw that in there. Now the feet are going to cancel, right, with the feet squared there. Then we're going to be left with the acres up on the top. We can also end up mentioning what that actual area is. That's going to be helpful for us in calculating out the lawns area. So let's go ahead and go 50 times 35. Then we got to divide that value by 43560. So 0.0402 acres, what we'll go to. We'll end up going to that 10,000th place there. And so that's what we got for the acreage. Now we can actually solve for the acres of this. Let's first multiply all this out though, since we have on our calculator this value for the area. So then we'll go ahead and take that times 2.44, multiply that by 0.95, and then multiply that by 1.1. And so what we're going to end up with here for our runoff, this is just from that shingle roof, 0.102. Remember, that is cubic feet per second. You can write it out in that manner, or you can end up just putting in CFS. That works also. But we're going to add these two up, and then also we need to add in the Q of the lawn, right? So we can find out the total post-development. Now, just as we were saying, we know the area now for the parking lot and the roof. If we take 1.5 and subtract those two areas, that remainder, or whatever is remaining, that's going to be the area of the lawn here. So we're going to go ahead and do down here, area of the lawn equals, and we've got the area of the parking lot. Actually, sorry, let's cross that out. Remember, anytime we make a mistake, just cross it through once, put the date and then your initials. So what we're going to end up putting down here is the total area. So it's going to be a total, right, which is that 1.5 minus the area of our parking lot, minus the area of the roof, and then whatever's remaining is going to be the area of the lawn there. So, just as we were saying before, 1.5 minus 0.2755 minus 0.0402, which, yeah, in terms of the acreage of the roof, pretty small. 1.184. We'll end up going out to the 3 there, just so that we're consistent. So it's acres. And so now we can end up plugging this value into the Q value for our lawn, right? So 1.1843 acres. Now we can multiply this out. So 1.1 times 0.175 times 2.44 times 1.1843. Perfect. And so now we've got 0.556, and then we'll call it there just because we went to the thousandths place for all these other values. And then for this one, just to show you guys, you can also use that unit, CFS. It's the same thing. It's just cubic feet per second. So that stands for. And so now we ended up finding out this post-development here. And as you can imagine, this is a pretty big value, especially in comparison to what our Q pre value was up here. It's 0.523. Just from the lawn alone, we've actually got 0.556 cubic feet per second, which already has exceeded our Q pre. And so now what we could do is we can add these up to find out what our total Q post is. And so we're going to go ahead and put that right here. So we're going to go ahead and take the parking plus the roof plus the lawn. We can find out what that total value is. So we've got the 0.702 plus 0.556 plus 0.102. In total, we've got 1.36 cubic feet per second for our post-development there. So remember, we don't want to exceed our Q pre. So now we can go ahead and calculate out delta Q for this particular question. So we can go ahead and put that right here. Delta Q is going to be equal to our Q post minus Q pre here, right? And so now if we plug in our values, it's going to be 1.36 cubic feet per second minus 0.523 cubic feet per second. What we're going to end up with here is 1.36 minus 0.523. And so now it is 0.837 cubic feet per second. And so that is our total change in peak runoff rate for this particular example. And so just as we were saying, you know, the engineer, we're going to come up with the stormwater management plan, because this can't be the case where we're increasing by 0.837 cubic feet. We want to try to get that as close to zero as possible. Alrighty, let's go ahead. Let's move on to question number 3. So they have, what is the estimated change in stormwater runoff for our affordable home site in Noblesville, Indiana? They want us to use a 100-year, 1-hour design storm. They want to assume that the existing site is flat with clay soil and unimproved with a runoff coefficient of C equal to 0.2. They end up telling us when calculating the post-development runoff for each of the following options, we must use the most conservative values, which means out of that range, we want to end up using that upper value, right? The greatest value we can end up getting. If you do that, that's going to result in the greatest volume of the stormwater runoff. So that's why we're playing that conservatively. So that's what we want to select for those runoff coefficients. They also say to use your current site plan as a basis for our calculations. And so they've got these two options here. So option 1 is going to be that there's no stormwater management. Okay, so just the case where the roof covered with asphalt shingles, The second thing is the driveway and the sidewalks, and also patio. If you do have one of those, that's just going to be a concrete surface. The third thing is the remainder of the site is to be planted with turf, grass, so no additional landscaping or also plant material. So that's going to be the first option. Then option 2 is where we have the low impact affordable home site design. Make sure that you know what all low impact consists of for your site. So first off, one of the things that are going to make this a low impact affordable home site design is you're going to end up having the rainwater from the roof actually be collected in either a rain barrel or a cistern. And what that's going to allow us is to not include the roof in our post-development stormwater runoff, right? Because we're going to end up capturing that water and then later using it for watering the lawn as well as the landscaping. Second thing for option 2 is the driveway and sidewalks and also patio, if you have that, are going to be constructed from permeable pavers, all right? The third thing is 50% of the turf area in option 1 is instead planted with native plant material. So if you use native plants, that is also additionally low impact design. Make sure that you remember these, what low impact design looks like for our site plans. All right. So keep those in mind. Obviously, guys, for the post-development, it's going to be particular to you and your actual site plan. You guys have differing floor areas, right? Because or we should say house footprints, right? Because that's the total exterior dimensions that your house is actually taking up on the site. Because those are different, as well as maybe even your driveways, any sidewalks that you have, your guys' values are going to differ completely for the post-development. And for that reason, I'm just going to be going through, I'm going to be showing you the pre-development, and then I'm going to trust in you all to be able to calculate out on your own that post-development runoff. So as you're doing that, make sure you're breaking it down. What are all the different types of materials that you have on your site? And then calculate out the Q value for each of those. Keep in mind, once you get to option 2, although the roof is one of your materials, since you are collecting all the rainwater from that roof into the rain barrel or the cistern, you're actually not going to include that in your post-development stormwater volume. Ensure that you are taking note in your documentation, though, that the reason why you're not including that is because we're capturing that rainwater in the rain barrel or the cistern. All right. Without further ado, let's go ahead. Let's get down to business. What I ended up doing is I wrote down some of the information that we were already provided, such as the return period of that storm, also the duration of that storm. Additionally, they told us for the pre-development that the C value we should be using is 0.2. You'll remember that that is the C value for that unimproved flat site with clay soil. All right. What we need to do now is we need to determine what is the CF value and what is the I value. So if we pop back into our engineering formula sheet, we'll end up seeing CF for a 100-year return period storm, the biggest value we can have, right? And so what we're going to put down in there is the 1.25. Okay. Up next, we want to find for Noblesville, Indiana, the precipitation intensity is the data type we want, and then we want the partial duration. Remember, we can end up typing this in by address. We'll also see on here, we do have good old Noblesville there. So if you also select that, you can end up doing that. You could also end up even putting in the address. We've had the site plan, right? You can end up determining where exactly is the site located. You could put that in and then use that. But what I ended up doing is I basically selected Noblesville here. We can zoom in even as well, so we can get even closer into Noblesville. It seems like that thing might have just kind of crashed out a little bit, but we do have the name Noblesville, Indiana on there. So now what I'm going to go ahead and do is I'm going to scroll down, and we've got to find for the 100-year storm that lasts for 1 hour, what is our I value? What I ended up just finding there is that our I value is going to be 3.04. Now remember, I value is in inches per hour, so inches of rainfall per hour. Keep in mind, CF and I remains consistent throughout this problem, right? The pre-development, we're going to be using it. Also, for the post-development, you're going to be using those CF and I values. All right. So we can go ahead and start to move on here. So the CFI values, we've got that. They also gave us 0.2, which is for that flat site that is unimproved with the clay soil. And then we just have to find out the area. So the area for our actual site is 0.5 acres. And so that was taken from the site plan. You'll remember CF and I we've got written up here. We also have C up here. And so now what we can end up doing is basically punching in all these numbers, right? So we've got 1.25, and then we can multiply that by C, which is 0.2. Then we can multiply that by I, which is 3.04. Then we can multiply that finally by our area, which is 0.5. And so let's go ahead and get the good old TI-84 emulator. So we've got 1.25 times 0.2 times 3.04 times 0.5. And what we ended up finding is our Q value is 0.38. Now, what is that unit once again? That is cubic feet per second. And so that's what we're dealing with there. Now, guys, this is just our pre-development, right? We want to find that change in peak runoff rate. So you do have to calculate out for post-development as well. Now, remember, post-development, we've got to take into consideration all the different materials, right? All the different surface types. So you might have roof, concrete. The land is also going to be improved, right? So you'll have to designate in terms of your lawn what is the case for you, right? They do have the turf, right? So you want to end up taking that into consideration. So for option 1, they have turf grass, right? For option number 2, that's whenever you end up using 50% of that turf area is instead planted with the native plant material. And so you'll have to reference this guy right here to find out what those values are going to be, all right? Ahead and finish this up with question number 4. Obviously, afterwards, you guys will also want to take a look at those conclusion questions. But question number 4, I like this question a lot. So what they're asking us here is, what size water storage tank would you recommend to collect the volume of water that would fall during the 24 hours of a 2-year, 24-hour storm on the affordable home? How would you install sufficient water storage? All right. So what we're going to go ahead and assume is that we are currently dealing with a 2-bedroom house. That means that our floor area is going to be 900 square feet. Okay. So what we are going to do is we're going to use that area in this calculation. Now, first off, I is what we want to be looking at. So they said for a 24-hour, 2-year storm. Okay. So as we move forward with this question, the one thing, this is what I ended up finding. I put in Noblesville, right? I clicked on there, and what ended up happening is this actually went back to that precipitation depth. And so you want to select that precipitation intensity. So the value that I was receiving for the depth, that was the total collected rainfall after 24 hours. And so after we have the actual rain precipitation intensity, then we end up with a value for a 24-hour storm that is a 2-year return period. We've actually got 0.118 is going to be our value. So I, in this case, is 0.118 inches per hour. And so this is where you want to be very, very careful, especially with throughout the entirety of this activity, that you are ensuring that you're selecting the precipitation intensity anytime you're trying to get I. Additionally, you should also have the partial duration there. And so we end up finding this I value, which is 0.118 inches, and that is per hour. So that's our rainfall intensity. Now, in terms of the total rainfall, that is going to be this value of 0.118 inches per hour. And we're going to multiply that by the 24 hours that rainfall is going to be coming in. Now, the hours are going to end up canceling in here, and let me make sure I'm popping back onto here before I get too far ahead, but this is our intensity, right? It's inches per hour. If we multiply that by the duration of this, we could end up canceling out the hours. We're left with inches of rainfall, and so this will end up giving us, if we pop into the good old TI-84, skip that back, 0.118 times 24, that's going to end up giving us a total depth of 2.832, and then that's inches of rainfall, right? So that's our total rainfall. Now, terms of doing all these calculations, what is your other option? If you go to precipitation depth, and then you ensure that you're in Noblesville, Indiana, you'll end up seeing for a 2-year return period storm, for 24 hours, we end up with 2.84. Now, is that basically what we just ended up getting? Yes, absolutely. And so now, since we know that there's 2.832 inches of rainfall, we can take our next step. So what we're looking for is a volume, right? And so this is just a linear distance here. What we can do is actually this. So volume of water, we can end up taking our 900 square feet, right? Because that's the actual footprint of our house. If we take that 900 square feet, we can end up multiplying that by this converted to feet, right? And if we end up canceling out all those units, we'll end up with a value of cubic feet, which is a volume, right? And so we've got the 2.832 inches. Now, if we multiply this by a conversion factor, there are 12 inches in 1 foot. We can end up canceling these units. And so what we're going to be left with are those cubic feet. And so now, let's go ahead and bring up the good old TI-84 again. TI-84, we've got the 900 times. We can end up using our answer, right? So if you go second, and then you press this guy right here, that's going to be the answer. And then we want to divide that by 12. Okay, so now what we end up with is going to be roughly 212.4 cubic feet there. And so that's the volume of the water that's going to be collected throughout the duration of that storm. And so now we can end up converting this from cubic feet to gallons, right? And so let's actually take a look at our engineering formula sheet. Let's see if there's any conversion to gallons. And let's make sure that we're putting this in here. Okay, nice. So let's go ahead, let's bring that up to 12.4 cubic feet to gallons. And so what we are seeing here is that it is 1588.86. Let's go ahead and let's call that, we'll say that that is approximately 1590. 1590, and remember that is gallons. And so the designation that we want to end up making is that a 16,000 gallon underground tank could be installed for this. Okay, so as long as we have the 1,600 gallon underground tank, then we're going to be good given these particular criteria. Now, the one thing that I forgot to do here is this was a new page for me. I'm going to make sure that I got the name on there. We want to make sure that everything is titled. So this is 2, 3, 11. What did I end up marking down my first page as? Stay organized, kids. So 2, 3, 11, we have calculating property drainage. Make sure that you've got this all updated in your table of contents too. I'm going to put on here part 2. In terms of the date, 10, 21, 20, 25, period. First, all right? So remember, this post-development, you'll want to make sure that you have that calculated out. Find that peak runoff rate, or the change in peak runoff. You're going to be taking Q post minus Q pre. I don't know what that value is. Anyways, hope this video was helpful. Thank you all for joining me on this journey into stormwater runoff calculations. Catch you all in the next video. Happy calculating. Bye-bye.